You're building a contact app. You write code to find Sarah Johnson in your phone's contact list. With 10 contacts, it takes a split second. You launch the app. It goes viral. Now you have 10,000 contacts. Suddenly, searching takes 15 seconds. Your users are furious. What happened? Here's what you need to know. The way your algorithm scales matters more than how fast it runs today. This is what Big O notation tells us. By the end of this video, you'll be able to look at any algorithm and predict whether it'll crash and burn or scale beautifully. Before we begin, don't forget to like, share, and subscribe to our channel. You already understand that some tasks take longer than others. Counting to 10 is faster than counting to 1,000,000. That's intuitive. Big O formalizes this intuition. Think of Big O as a growth chart, like tracking a child's height over time. We're not measuring exact height today, we're measuring the pattern of growth. Will they grow slowly and steadily, or shoot up dramatically? We use N to represent input size. How many contacts, how many numbers to sort, how many items to search through. Big O answers the question, what happens to runtime when N doubles? Imagine a filing cabinet with numbered drawers. You want the paper in drawer 5. Do you open every drawer? No, you go directly to drawer 5. One action, regardless of how many drawers exist. This is Big O1. The code runs in constant time. Whether you have 10 items or 10 million, it's always one operation. An example being an array of 5. One lookup, done. Now imagine you need to find a paper, but you only remember it's blue. Now you must open every drawer and check. If you have 10 drawers, that's 10 checks. If you have 100 drawers, that's 100 checks. This is O of N. The time grows in a straight line with input size. Double the input, double the time. An example is finding the largest number in an unsorted list. You must check every number. This is where it gets interesting. Imagine a phone book with 1,000 pages. To find Sarah Johnson, do you start at page 1? No, you open to the middle, page 500. You see Martinez. Sarah comes after that, so you ignore the first 500 pages. You open to page 750. You see Roberts. Sarah comes before that. You've now eliminated 750 pages with just 2 checks. This is O of log n. Each step cuts the problem in half. With 1,000 items, you need only about 10 steps. With 1,000,000 items, you only need about 20 steps. This is binary search. It's extremely powerful. Picture a classroom with 10 students. Everyone must shake hands with everyone else exactly once. How many handshakes? Student 1 shakes 9 hands. Student 2 shakes 8 new hands, and so on. That's 45 handshakes in total. Now imagine 100 students. That's about 5,000 handshakes. See what happened? We multiplied students by 10, but handshakes multiplied by 100. That's O of n squared. An example is comparing every item with every other item. Nested loops in code. Let's lock this in with a visual pattern so you never forget in the future. The speed ladder. Visualize climbing in complexity. Draw a ladder with rungs labeled bottom to top. O of 1, 1 step, done. Green checkmark, flat horizontal line. O of log n. Cuts in half each time. Blue, splitting arrow. Gentle curve, barely rising. O of n. Checks everything once. Yellow straight diagonal. Steady 45-degree line. O of n squared. Nested loops nightmare. Red explosion. It's a steep curve shooting upward. Ask yourself, when my data doubles from 100 to 200, what happens? O of 1. Still one operation. It doesn't care about size. O of log n. Goes from 7 to 8 steps. Barely notices. O of n. Goes from 100 to 200 operations. Doubles with data. O of n squared. Goes from 10,000 to 40,000 operations. Quadruples, danger. Let's draw the graph one more time with memorable shapes. O of 1 looks like a flat road, smooth sailing forever. O of log n looks like a gentle hill, easy climb that levels off. O of n looks like a ramp, steady, predictable incline. O of n squared looks like a cliff, suddenly becomes vertical. O of 2 to the n, it shoots off the page. It's practically infinite. Here's a quick traffic light system, so you know which one is more okay to use and which one should be a last resort. In the green zone, O of n and O of log n. You can use these no problem. In the yellow zone, O of n and O of n log n. Acceptable for most cases. And in the red zone, O of n squared, and worse. Avoid unless n is tiny. Here's why this matters in the real world. Google searches billions of web pages in milliseconds. They're using O of log n algorithms. Facebook sorts your newsfeed from millions of posts efficiently. O, n of log n algorithms. Your banking app processes transactions securely without lag. O of n at worst. Bad big O is why your computer freezes when sorting 50,000 photos using a naive algorithm. It's why some apps feel instant while others feel sluggish. Here's a quick recap. Match the scenario to big O. Looking up a word's definition in a hash map? O of 1. Finding a name in a sorted phone book? O of log n. Finding the oldest person in an unsorted room? O of n. Comparing every person's age with every other person? O of n squared. Now you can predict whether your code will scale or fail spectacularly. Remember, choose your algorithms wisely. Thanks for watching.